right, welcome. This is our Thursday edition, and we are asking ourselves, what does light oscillate? Every wave has to oscillate some material, and there is an answer to that question, although it does seem confusing. In air, you'd think it would be air molecules that were oscillating, but we all know light travels through space where there is no air, or very little molecules. So what does light oscillate? And the answer came from a man named Maxwell. His name was James Maxwell. And before he came along, people said, oh, we know what oscillates. It's ether. It's like, they kind of made up. They said, there's ether everywhere, and that's what oscillates. But we have no indication that there's anything out there called ether. So, on that idea. So James Maxwell came along, and he said, I know what oscillates, and he shared it with us, and it was the electromagnetic fields. Every planet, everywhere in space, there are electrical and magnetic fields, and that's what oscillates. So let me give you a handout. You don't have to write it on that sheet. We're on to the next one, sort of. And let me show you on the board. Then I'll give you this sheet where I drew it out for you, or copied it out for you even clearer. It turns out that the electrical field, like imagine this is a floor. I'm not very good at drawing, but this is on the floor. So it's flat. It's hard to draw perspective. So that is flat on the floor. That would be the electrical field, and it also oscillating at right angles to it is the magnetic field. So these are coming up out of the floor and going under the floor, up out of the floor. So these are, it's hard for me to draw, so that's why I copied it. These are at right angles to one another. All right. Their copy is better than mine, so I made it for you. All right. Light. We're talking still.
Wow.
I called this day 5B because 5A was light as a wave. We're still finishing that up on this. As you can see, I drew a picture of light as a wave. And do you see where the pointers point to the electric field and it points to the magnetic field? And they are at right angles to one another. So it's like a double wave according to Maxwell. The yellow wave is at right angles to the blue wave. Can you pick that up with your eye?
It's still in 3 dimensions.
Yeah. Hard for me to draw on the board. It didn't come out quite as good on my picture as it did on here. So, alright. So that's the general accepted view of light as a wave. So we were happy with that for so long, and then it acted like wave because we could use this formula, and we will use this formula, the one we use for sound. We're going to use it for light, but then also we saw that if it's a wave frequency, how many crests hit this per minute? The frequency. What was frequency related to sound? Do you recall, Alex? When sound waves, sound, not light, but when sound wave frequency goes up, what goes up? Remember we studied Doppler. What is it about the number of waves that hit a spot per minute? What goes up in sound as frequency goes up?
Is it the hertz?
It is measured in hertz. But what quantity changes to your ear? What do you hear differently as frequency goes up? It's not volume.
Oh, pitch.
Pitch, right. So frequency is related to pitch on sound waves, and amplitude was volume. But in light waves, so here's a light wave, frequency is related to color. Did you know? You've probably seen that in the past. Every color has its own frequency. It's different amount of wavelengths and frequency. So frequency with light is associated with color. Anyone know what amplitude remember the day I yelled at you? That was what amplitude affected sound. Amplitude affected volume of sound. So what do you think it affects in light? Any ideas? It's, what can we vary about light except the color?
The intensity?
Yeah, it is intensity. Amplitude is how bright or intense it is. So intensity or brightness, I'll call it. So it seems like we're rolling right along with this wave theory, and this formula works with it. And that has a lambda, which is wavelength, so everything is pointing to A-OK. So let's actually do a problem before we muddy the water. We're going to muddy all this up in a second. The reason I want to talk about this formula in relation to light is velocity, wrong V. Velocity is always the same in all of these problems, whether it's blue light, red light, all kinds of light. It's all going at the speed of light. So V is always the same. Do you remember from yesterday, MK, what the velocity of light is? It's
3.0 times
10 to the what?
8.
Yep, and that's meters per second. That's one we have to memorize for this class. So no matter what, notice when we were working with sound, that V was different in every problem. But in light, it's always that number.
I got a question. Why is there never mind. I thought there was toothpaste on the wavelength on 10.
What?
Toothpaste on 10.
It looks like toothpaste.
Yeah, on
Yeah, what is that?
the yellow
It's a
thing.
sunscreen.
This sunscreen. It's ultraviolet light with the toothpaste.
I
was like, why is toothpaste yellow?
I didn't think it was toothpaste, but I did know what in the world it was. Okay, well you figured it out for me. Yeah, we'll get down to that in just a second.
Well, the reason why light never changes in its velocity is because the medium that which oscillates through doesn't change. It doesn't change in its nature.
It doesn't. It
Whereas,
doesn't at all.
depending on the temperature, how much air there is
It doesn't
in the
matter.
field, it would actually change the form of the medium. It's not
Right,
relevant.
exactly. So it works a little different from sound waves in that way. This is not going to change according to temperature. It's always